Today we start the third part of our semester. In this part, I will discuss some limit theorem in dynamical systems. So this is our goal. Of course, I will start with a long introduction to discuss what are limit theorems in this context and how one can expect such things. So today it will be some sort of crash course in ergodic theory, and I hope limit theorems will appear at the next week. I plan to have four classes, and I plan that all of them will be online. So as usual on this Zoom conference and so on. Okay, so what I would like to discuss. So the ergodic theory is more or less the study of dynamical systems that have some invariant measures. So you can study, for example, dynamical systems where you have some space, and what is a general dynamical system? You have just a map of some space to itself. And of course, if this X is just a set, then it is not interesting because you have not enough structure, and the study is quite trivial. So in the set, you have either periodic orbits or not periodic. And of course, there can be some more delicate situations when T, for example, is not invertible. But nevertheless, this situation is too simple to study. Another sort of questions we can study is when T is, for example, homeomorphism or a discontinuous map, or when T is even better, it is a diffeomorphism or something like this. This is so-called smooth theory of dynamical systems and so on. And in ergodic theory, we study the situation when X is a measured space. So we have X B mu is space with measure. This means that B is a subset. So it is a sigma algebra, and mu is the measure itself. I hope this is quite well known. One more requirement that theoretically can be omitted, but we will always impose it, is that mu is a probability measure, a probabilistic measure. So mu of X equals 1. This, of course, if mu of X is something finite, this is not interesting. You can just scale down mu. But the case of infinite measure mu is of some interest, but again, we will just hold ourselves to the case of the probabilistic measure. So what does it mean that T conserves mu? Well, this means that the measure of every set is does not change when we apply T. The formal definition is a bit trickier. It says that for any measurable set, any set in B, you have that T, mu of A equals to the mu of T minus 1 of A. So the difference, the key point is that we have T minus 1 here instead of T. So why this is so? Well, first of all, if there are two reasons. One of them is just formal. You can say that T from xb to xb is measurable. This means that for any A in B, T minus 1 of A also belongs to B. This is just a definition of measurability, that pre-image of any measurable set is again measurable. And also there is a reason that is more, how to say, more explicit. Let us discuss some examples of invariant measures. So it's so this is the same thing, can be also expressed as mu is T invariant. This is the same. So some example of transformations and their invariant measures. Well, the first example is the following. So X is a circle, and I would like to think about circle as the factor space R over Z. So you just take the real numbers and say that two of them are equivalent if the difference is integer. In other words, you just take, this is just the same thing, you take the segment from 0 to 1 and factorize that 0 is, you just identify its ends. So you take from the interval, you take a circle. And on this space, let us consider the map R alpha, which maps X to the X plus alpha. So in terms of the real line, it's just a shift, and on the circle, it is maybe better to be described as a rotation. Yes, so you just rotate it by alpha of the full turn. So if, for example, alpha equals 1/2, you just turn the circle at 180 degrees. Then U is the Lebesgue measure. You can think, for example, that this is a Lebesgue measure on the unit interval, and the gluing of point of its ends doesn't change anything. Then, of course, you have this condition, so this measure is invariant. Well, not this one. This one. Well, the next example is more complicated. It is the so-called doubling map. So this is a rotation. And this map maps every point to X to the 2X. It is clear that our identification works well. It is still a continuous map on a circle. What does it? How can you describe it? Well, if this is your circle, then you do like this. So it just maps it into something like this. So here is the original circle. And you map everything back to the circle. So you just stretch it so it is became 2 times larger, then you twist it around itself. So we have 2 turns, and then you just put it back on the original circle. This is how it works. So, for example, if you take a point somewhere here, then the angle is double, so it is about here, and so the image is this point on the circle. And the measure, again, the Lebesgue measure is conserved by this map. If you decide to write TA here, then this is, of course, this cannot be expected from such a map, because for any segment, its image is 2 times longer. But with pre-images, everything works well. Let us check. For example, for of course, when you check this this condition, there is a standard machinery that, for example, here you can just check this for example, segments, because if this holds for segments, then you can say that it's also true for the union of segments. So then it even for infinite unions, so countable unions, and so on. So in fact, you can say that the all sets that are such that their measure is conserved under so the set of all A such that this holds is a sigma algebra. This is quite easy to prove, and therefore, if ever the sigma algebra that contains all segments contains the whole Borel sigma algebra, and if you want a bit more. And usually we just stop at Borel and say that in our examples, B is Borel. But of course, the last step that is sometimes needed is a completion of sigma algebra. So you just say that you include into the sigma algebra all subsets of the set of measure 0. And say that they also have measure 0. And then you just again take the usual operations with these sets. So this is not so important. But nevertheless, you just let us check that the measure of the pre-image of every segment is the same as the measure of the segment itself. So let's consider a segment. For example, here. Then what is its pre-image? Well, you can see that this pre-image contains of 2 segments. And if you draw it at the original circle, when you not stretch it, but take it at its original length, then this is something like this. And each of this, so there are 2 segments of half a length. So in total, they have the length equal to this segment. So let me write it down. So if A is, say, alpha beta, then let's say this. T minus 1 of A is the union of 2 segments, this one and this one. And therefore, and so the measure of A is beta minus alpha, and the measure of T minus 1 of A is beta minus alpha over 2 plus the same. So they are equal. Okay, so this is another example. of course, there are much more, and we'll discuss some such examples, I guess, even today. But let us just now consider these two. The next thing is the fundamental notion in the ergodic theory, and it is the so-called ergodic averages or ergodic sums. Take any point and take, let's start with some function f from, it is, for example, from the space L1 of x mu. I'll just, for brevity, will omit b in such notation, but of course, there is always the sigma algebra behind the measure. Okay, so you have the integrable function, or at least just a measurable, it doesn't matter now. And then you can consider, we can construct a new function, or even the sequence of functions. So this is a new function, and its value at the point x is the sum of from, it goes like this. And also it is quite convenient to take, to normalize this notation and take this one. So then how can you explain this notion? You just take the point and the first n points in its orbit, and you take the average of the values of function in these points. So these are the ergodic sums or ergodic averages. And one usual, you can think about this as follows, that you observe the life of one point for a long time, for time n. And then you just consider how often something happens. For example, if your function f is just the indicator function of some set, then Sn of this indicator function is the fraction of time that your point, or its, again, its images, belongs to this set A. So if f equals to 1A, then, for example, Sn A is the well, of course, so time. Of course, now the time, the duration of this observation is finite. It is n. But the natural question is what happens when n tends to infinity? Is it true that, for example, these fractions stabilize, so they have some limit, or maybe they will fluctuate indefinitely? So for any, so there is no limit, or maybe something more interesting happens. This question was raised even before the strict mathematical theory. It was this question was first studied by Boltzmann, who discussed this when he studied kinematic theory of gases and the corresponding thermodynamic So he asked how one can deduce thermodynamics from just simple mechanics. So if you have just a gas of particles, for example, elastically colliding with each other, and then what happens? Why, for example, the temperature stabilizes? So that if you take some very hot molecules and some cold molecules, then finally, so after some time, you have that all molecules have more or less the same speed, or more precisely, there is some distribution of speeds. That doesn't depend on the initial distribution of speeds of these molecules. This was his question, and so he said that it is natural to believe that there is this averaging, so that this it is natural to believe that these fractions, that these averages stabilize when n tends to infinity. And mathematically, this was proved somewhat. We'll maybe discuss what is the difference between this general hope of Boltzmann and strict results a bit later. But the results of this sort were obtained in 1930s, and we'll discuss today two of them. The first theorem is von Neumann's Ergodic Theorem. Says the following. So assume that f, so again, so we have x mu, t is mu preserving, and let us say that f belongs to L2. Not to L1, but a bit more. F belongs to L2 of x mu. Then Sn of f, so the sequence of ergodic averages, converged in L2, converges in L2 to Pf, where P is the orthogonal projection to the subspace M of all invariant function. So this is the statement. Okay. So let us discuss the proof. So maybe I'll just start with some comments. The first comment is that if you consider the map F, F in composition with T, it is quite clear that this map conserves, for example, any LP norm. So the norm of F LP equals to the norm of F in composition with T and LP for any P. Well, it is, in fact, this is just the change of variables, change of variable in the integral. So when you take the integral x of f x d mu of x, then because your because our well, because so you can just say that ty equals to x, and then you have change of variables, and this change of variables, it doesn't change the measure, because you know that T conserves measure. So if you don't believe it, this start, for example, with an indicator function. By the way, what is the indicator function in composition with some T? It is again the indicator function of what set, by the way? What should I write here?
T of A, or T minus 1 of A.
Right, T minus 1 of A. Well, because, so let's write it down. So 1 of A of T of X. This equals 1 if and only if Tx belongs to A, or that X belongs to T minus 1 of A. So this is, so we have this. So for this function, it is clear that the integral of this function, of the function 1 of A, which is just mu of A, equals to the mu of T minus 1 of A, which is integral from A in composition with T. Then therefore the same is true for their linear combinations, and then you just take some sort of limit. For example, you can say that start with, for example, with non-negative functions and consider the convergence, the monotone convergence, and apply, for example, Levy's theorem. And so this is so anyway. Even if you don't know how to prove this change of variable result, this is quite clear. So the corollary is that, for example, for L2, this map is the unitary map. So this is a unitary operator. This is exactly this property. But of course, in L2, you can just consider not only norms, but the products, the scalar products, and say that Fg equals to the Uf Ug, which is just F in composition with T, G in composition with T. So here, again, if you want to prove this, you just, this is again just the change of variable in an integral. You can do it by yourself. Okay, so this, for example, this means that the norm of this operator U is not more than 1. Every function is not stretching under this operator. And so if you take now the Sn, then Sn is 1 over n of the identity plus U square plus U to the n minus 1. And so, for example, it is easy to see, because the norm of every summand is not more than 1, then the norm of the whole is also not more than 1. In fact, in any LP again, and in particular for L2. So these were some preparations, and let us now discuss the proof. The proof is the following. We try to construct the orthogonal complement to M. M is a set of all F such that F equals to F of T. So this is a set of invariant functions. So F, so space of invariant functions. And what is its orthogonal complement? Then the answer is n, which is the set of all. Let me write this as follows. It is a closure of the of this. So you just take this difference, g minus ug. I'll show now that so claim that the orthogonal complement of n is m. Let us try to apply our averaging process to the element of n, by the way. So it is clear that you have many cancellations here. So you take 1 over n. This is not the proof of the claim. It is just the explanations. Why do we have this this subspace? So it is just g minus ug plus u, g minus ug. And when you redistribute all this, you have this. So everything cancels out except for the first and the last term. So this means that, for example, the norm of Sn of g minus ug is not more than the norm of g, well, let's say multiplied by 2 over n. And therefore, we have convergence for such functions. So for such functions, we have a straightforward convergence to 0. There is no difficulty. On the contrary, for the function, so if f belongs to m, then Sn of f is just 1 over n of f plus f, which is the same as uf, plus f, which is u square f plus f. So it is just f again. So here again, everything is trivial. We have convergence to f, exactly, which is exactly the same as we prescribed, because we said that the convergence should be to the projection onto the m, onto the space m. So for the elements of m, we have the convergence to the element itself. So the question is, where is the difficulty? So assume that we have proven this claim, and then, for example, from this claim, it is clear that for any element of n, the PF is 0. Yes. PF equals, let's say PH equals 0 for any H, because P is the orthogonal projection onto M, and therefore all the complement maps into 0. So are there any cases that were not discussed in terms of convergence? So this was the case of the difference, g minus ug, and this is the case when f belongs to m. Are there any uncovered cases?
Sorry, I lost the point. What we are trying to cover?
Well, what do we want to prove? So let us revisit it again. It is here. We want to prove this. So we want to prove it for f belonging to L2. If we believe now in the claim that was stated, then I can say that this is M direct sum with N. So that M and N are orthogonal, and so every element and their sum is just the whole space L2. Now I want to prove this. So this is my goal. Of course, any function can be decomposed into the some part that belongs to M and some part that belongs to N. So let's take some function f and let us decompose it something like this. Well, just fm plus fn. So now, of course, as n is a linear operator, so we can consider fm and fn separately. For fm, so fm belongs to m. So, and by the way, pf is just fm. So we want to prove that Sn f converges to fm. Part 1. Consider Sn of fm. And this is just fm, and so there is a convergence to fm. The second part is, so it remains to prove that Sn of fn converges to 0. And so for any function from n, we want to prove that Sn of this function converges to 0. So it seems that this was the proof. But I state that this is an incomplete proof. Why is it so? Well, the answer here is in this closure. Because when we are in infinite dimensional situation, so it is not true that when you take the linear span of some elements, then it is a closed subspace. And I want to deal with only with the closed subspaces, because only for closed subspaces the natural geometric arguments work. For example, this our idea of the orthogonal complements. So I take the closure of all such elements of the form G minus UG, and therefore I just want to consider not only the elements of this form, but also their the elements from the closure of this, so the limits of such elements, and so I want to consider, so H is the limit, so let's say GK minus UGK tends to some H. So H belongs to N, therefore there exists GK such that the convergence is, of course, in our norm, in L2 norm. So then we can take some approximation. We can, for example, say that so for any epsilon, have that h equals to the gk. So there exists k. That. And the norm of hk is less than epsilon. So just take tilt. So if gk minus ugk is close to h, then the difference has a small norm. And I take k sufficiently large so that the norm of this difference is less than epsilon. And then what do we have for Sn of h? This is Sn of gk minus ugk plus Sn of h tilde k. I have already said that Sn, the norm of Sn is not more than 1. It is not expanding. So the norm of this function is less than epsilon, just because of this. And the norm of this is not more than the norm of gk times 2 to the n. Therefore, if you want to say that for all n larger than some n not of epsilon, you have that the norm of Snh is less than, okay, let's say delta. So this is what you want to prove. Yes, so that for large n, the norm of this average is small. How do you prove this? You just, so you take this delta, take epsilon equals to delta over 2. Then you choose k from here. And then for this k, you have that, and then you take n and not of delta is more than epsilon over 2 norm of gk. So therefore, for n larger than this and not, you have that the norm of this will be not more than epsilon. Again, the norm of this is not more than epsilon, and therefore the total norm is not more than 2 epsilon, which is delta. So this is the end of the proof. We have concluded that for any function we have the convergence to Pf, and so the only white some blank point in here is this claim. So up to this claim, the proof is complete. Let me repeat it again. So if so we just decompose our function to the part that belongs to M and the part that belongs to its orthogonal complement, which is N. Then for M, the situation is clear. The averaging doesn't do anything with this with such functions. And for the complement, we first prove that for the elements of the form G minus UG, you have convergence to 0. And then you prove that for limits, that is for closure, you have also this convergence to 0. And that's it. So let us prove of the claim. So I want to prove that orthogonal complement to N equals M. So let's try to consider the, so first, consider some element H that belongs to this orthogonal complement. This means that for any H, for any G, H G minus G equals 0. By the way, here there is no need to consider also the limits of such elements, because the scalar product is continuous. So if this is true, then for limits we have also this. So let's rewrite this as follows. So this is H G minus equals to, well, I just want to put to move this U to the other part. So you have just H minus U star H over G equals 0. And therefore, you have the element H minus U star H, which is orthogonal to everything. Therefore, for example, it is orthogonal to itself. Therefore, in G, we have this H minus U star H equals 0. Or I want to prove that so I want to prove that H belongs to M, so that H equal to UH. And this is done as follows. You just consider the norm of UH minus H. And this is write it down here. So then I shift this U to the other side, and you have this. And finally, I do the following. I just, and this is H, because I know this. So this is H, and you have the norm of UH squared minus the norm of H squared. Note that the U is non-expanding, so its norm is not more than 1. Therefore, UH is so in fact its norm is exactly 1, so it is just an isometry. Therefore, UH equals so this norm is also the same as the norm of H, and so it is 0, and that's it. So we have proven that this equals 0. And this means that H equals UH, or H belongs to M. And for the converse implication is more or less the same. So let me try to write it down. So if H belongs to M. This means that UH equals H. And by the same argument, U star H equals H. The same argument, but for U star against instead of U. And therefore, you can write it down that H this. You can just read the previous formula backwards. So this is 0. So we see that H is orthogonal to M. So this is the same. And therefore, the claim is completely proven, and the whole von Neumann's ergodic theorem is also proven. Let me now discuss another result, which is maybe more, it is less geometric, so it is maybe difficult. So here is just, as you see, it's just some geometry of Hilbert spaces, nothing more. And the another ergodic theorem, it is Birkhoff ergodic theorem, is more or less the same, but for the convergence almost surely, for pointwise convergence. Let me write it down. So again, we have probability space. We have again the measure preserving transformation, and F belongs to L1. Then we have the following. First of all, S and F converges almost surely, or almost everywhere, if you wish, to some F prime. So there exists F bar such that the second part is that this function F is invariant. This means that F bar of Tx equals bar of X, again, almost everywhere. The third is that for function in L1, the resulting function is also in L1, and the norm of this function is not more than the norm of the original function. Fourth statement is that the convergence here is in fact in L1 also, not only almost everywhere. And the fifth statement is the following: for any A such for any invariant set, that is that its preimage is itself, we have that the integral of the original function over this A is the same as of this limit function. So this property, or in fact property 2 plus 5, means the following: that if you consider the family of invariant sets, then this is a sigma algebra. This is just a direct direct observation. You just see that if you, for example, take the complement of the intersection of two such sets, then it is again an invariant. And for the countable union, it is the same. So this is a sigma algebra of invariant sets. And then 2 plus 5 just says that the function f bar is the conditional expectation of f with respect to this sigma algebra. Because if you recall the definition has two parts. First part is that it is measurable with respect to G, and this is just a property number 2. It says that on every that the set of X such that F takes some value or some values in some subset is T invariant. And the second property of conditional expectation, the second part of its definition, is that for any set from our sigma algebra, the average of the integral of f and of the conditional expectation is the same. And this is the property number 5 here. So this can be expressed just like this. So maybe I will let me discuss the proof of this statement also. It is, in fact, there are many proofs, and unfortunately, there is no such a straightforward proof as for Ergodic theorem. Every proof has some sort of trick inside, and some of these tricks became the well-known tricks, maybe even the methods. And so the proof I'll explain is based on so-called maximal ergodic theorem. That was it was not the original proof by Birgov. This proof was just about a decade later, and so the idea is the following: consider the following function. So let us assume that let's consider the following function, which is you just take all the averages of this function and take a supremum of all of this. Then sometimes it is more convenient to take not the supremum but the upper limits, lim sup. But let's prove with this. So theorem says that the integral of our function over the set when f star is positive is non-negative. So this is a statement. Again, I will omit the usual part that we have the probability space, we have the transformation that preserves this probability measure, and that function f belongs to L1. Then so this is what I want to prove. Let us maybe, okay, so let me explain how to prove the statement of this sort. Consider the set, so we say that f star is positive. This set is disjoint union over all n of the sets Bn, where Bn is the set of all x such that S1 of x is non-positive, S2 of x is non-positive, and so on up to Sn minus 1 of x, and only Sn of x is positive. So because if the supremum is positive, then there is an element that is positive, and let's take the minimal number such that Sn of f is positive, and the set of all x's where this minimal number equals to n is denoted by Bn. So I want to show that the integral over the union of the first n of this is again non-negative. Then this is clear. This is just the usual, so the dominated convergence theorem, for example, also because the function f belongs to L1. So when you extend the interval of integration, you have just the convergence of the integral. So this is again trivial. So I want to prove this. And for simplicity, I will again also just I will assume that T is a bijection. You can figure out how it's a general case, but it is maybe a bit easier to follow all the details. Let me start with the following observation. I want to say that Tk of Bn belongs to the union of these guys when k is not more k is strictly less than n. Why is it so? So if you belong to this, this means that so if x belongs to this set, then x is Tk of y, where y is y belongs to Tn. Yes, and therefore we have the following, that I'm sorry, here of course I should write this because f is it is fixed, but it is still in the notation. So let us say that y belongs to Bn. In particular, this means that y, f of y plus f of ty plus f of Tn minus 1, y is positive, while if you take the sum of the lesser of some shorter sequence, and in particular the sum of the first k of them, and this is non-negative. Therefore, we have that the sum from the number k to the number to the end is also positive, because we just subtract some non-positive part, and therefore this is even more positive than the previous one. And this is just f of x plus f of n minus f of t n minus k of x. And therefore, this sum for the point x is positive, and of course there's maybe also the sum with the smaller number that is also positive. But so if you take the sum with the smallest possible number, then you take you see that this x belongs to the right hand side here. So we have this inclusion, and now we can consider the following. So by the way, let us also consider now these sets, and I want to say that the sets. So the next step. The next step is that Bn, T, Bn, Tn minus 1 Bn are disjoint, pairwise disjoint. So why is it so? It is because if two of them intersecting, then we can shift one of them to the bottom. Say, for example, if I is less than j, then Bn intersection with this is also non-empty. And this is not possible because this belongs to B1 to Bn minus 1. And we know that Bn's are disjoint. So therefore, we have seen that we can pull out this part of the set. So we take. So let us write it down as follows. So my idea is to rearrange. Let us recall that I want to prove this. So I want to cut this union into some chunks such that for every chunk it is clear that this integral is non-negative, and the first chunk is indeed constructed. So let me write it as follows. So B prime n equals to Bn, and Cn equals to the union of all these guys. So it is Bn, maybe Bn prime. This is the same. Then it is clear that the integral over Cn of f d mu is this is a sum of the integral over tk prime f d mu, and again we make a change of variables, and so this is from k equals 0 to n minus 1, and therefore we have the integral over b prime n of f. So I write it like this, and here I write it like this. Here y equals to the tk of x. And so this is, and here I want to join the integrals again. So now the set where we integrate is the same, and so I put the sum inside, and inside I have f of y plus f of ty. Oh, I'm sorry. This is like this. And this is in fact positive, or maybe non-negative, because let us recall that this is positive in, maybe just a moment. Yes, this is positive in Bn, and B prime n is its subset. Well, the next step is the following. So I take the B prime n minus 1, which is B n minus 1, minus everything that was already used, so minus Cn. And Cn minus 1 is the union of B prime n minus 1 and now to Tn minus 2, Bn minus 1 prime. Again, all these guys are disjoint, and it's important to state that this again, this belongs to the union of these levels. So so the first level is belongs to Bn minus 1, and the rest belongs to the B's even with smaller numbers. But nevertheless, I want to say that Cn minus 1 does not intersect with Cn. Then after this step, I, on the one hand, construct again a set. So then it is again the integral over Cn minus 1 of f d mu is negative, and so on. I guess the rest is quite clear. So at any step, so let me. But this is now is a mystery bit. So then I write B prime. So I iteratively write B prime m is Bm minus Cm plus 1 Cn, and Cm is B prime m this is the general construction, and the only difference is the only question is, why do all these sets not intersecting? Let me draw it like this. So here is B prime n, and this is Cn, and so our map acts as a shift above. Then I take B n minus 1 prime and take its images, what one less, and so on. And so here is B prime m, and so on. So assume that two of these levels intersect. So assume that some point belongs, for example, somewhere here and somewhere here. So let me introduce some names. So it is, in fact, the collections of sets of this sort are quite ubiquitous in ergodic theory, and so usually this set is called tower, and each individual set is level. So maybe it is better to call it a skyscraper, but the traditional name is tower. I want to prove that all levels of all towers do not intersect. What I have already know. First of all, I know that the levels of the same tower do not intersect. This was this was proven just a few minutes before. Here, and of course this proof does not since of course we can prove this not only for n but for any index, and since the base of the tower b prime m is just a subset of bm, then the same holds for b prime m also. Then we can say that if there is an intersection, then these points are in different towers. Okay, then let us, so we have two towers, we have two, say this purple point is the same. Then we can take its pre-image until some of the points go to the ground level of some tower. So, for example, we can have this situation when so the ground level of one tower intersects with some level in another one. Well, first of all, the situation as it is drawn now is impossible, because b prime m by definition is bm minus everything before, minus all the towers before. So this can't happen. Now, the opposite situation is when the point at the ground level of the tower with larger number coincides with the point somewhere here. Why is this not possible? This is not possible because all these levels belongs to the bm minus 1 and so on to b1. This is again our first inclusion, because b prime m belongs to bm, is a subset of bm, then its images are the subsets of this set, and therefore and this ground level is a subset of b and bm minus 1 here, and therefore there is no intersection because dj's are disjoint. So all levels of all towers are disjoint. And b1 and so on to bn, we can just say like here, is just the same as the union of c1 cn, and we know that the integral over cj of f d mu is non-negative, and therefore the whole the sum of the integral over the union is also non-negative. And this ends the proof of the maximal ergodic theorem. And now let me show how to apply this to prove the ergodic theorem itself. Maybe I will skip the details, but prove only the key ingredient, the first part, that the first statement that says, first statement says that, just a moment. This one. So this is the most interesting part. It says that for almost every point there is convergence somewhere, and then we try to explain what is something about this limit. But this is in fact the key statement here. Okay, okay, let me prove it here. Well, first of all, some corollary of the maximal ergodic theorem is the following: that the integral over the set where this f star is larger than alpha of f d mu is not less than alpha times the measure of this set. This is just the original statement, but for the function g, which is f minus alpha. Yes, because when you take this g, then you you can just put this as an integral of alpha over the same set, put it to the left and take the integral of g, and then you can observe that f star and g star are also related by this. So this is trivial. Okay, so let us consider the following set. So take a proof of in Ergodic Theorem. I just want let us consider the set where of points such that for our function there is a difference. So, for example, the lower limit is less than alpha and upper limit is larger than beta. What I want to say that so first of all, if let us consider also the set E, the set E such that the limit does not exist. Yes. Then this set is just the union of all E alpha beta, but we can also say that it is a union of all E alpha beta only for over alpha and beta belongs to Q, to the rational numbers. Of course, alpha less than beta. Because so if the limit does not exist, then the upper limit and lower limit differs, and therefore between them I can put two rational numbers, alpha and beta. And so then such point x belongs to E alpha beta. Well, then I want to, so it remains to prove that the measure of E alpha beta equals 0 for any alpha beta. Okay, the first thing is that E alpha beta is an invariant set. in fact, maybe I should write it down even before, but let us consider the point x and the point tx. What can we say about the difference x and we have tx? We can compare, for example, the Sn f of x and for Sn minus 1 f of tx. Well, how one can compare these two values? Well, first of all, these values are related as follows. So this is this plus f of x over n. And therefore, so we can see that this tends to 0 and this tends to 1. And therefore, the lim sup of the left-hand side is just the same as the lim sup of these guys, and this lim sup is the same as the lim sup for S and F. Yes. So we see that these ergodic averages are almost invariant, and therefore here we need to write it down in this form. You can see that this set E alpha beta is invariant, and therefore, since it is invariant, we can consider that the set F star is larger than beta. And let's consider, so and E alpha beta is here, subset. And we can consider T restricted to this E alpha beta. So again, we consider E alpha beta and mu restricted to this E alpha beta. This is not the probability space. This is a space with measure that is also finite, but with some other constant. One can check that all that is written down is not changed when we rescale the measure. So I don't need to divide this measure by mu E alpha beta. Everything works even without this scaling. So what we have is the following. This one. Well, this is just this corollary for beta instead of alpha. Recall that for the entire our space E alpha beta, we have that F star is larger than beta, or in fact, it is not only supremum larger than beta, but lim sup is larger than beta. So we have this. And for minus F, we have the same thing, but for so we can write it like this: alpha beta of f d mu of minus f d mu is larger or equal than minus alpha mu of this. So now and so for minus f we have minus f. Well, let us write it down as follows: E alpha beta is a subset of minus f star larger than minus alpha. And so we have this. or we can rewrite it as the integral of f d mu is less than alpha. And that's it. So we have seen from these two inequalities that alpha times the measure of this set is not less than beta times the measure of this set, while alpha is less than beta. And this implies that the measure of our set is 0. And that's it. Well, this completes the proof of the item 1 here. And for example, item 2 is again the same argument that for the ergodic average for SNF, this is almost true, and therefore for in the limit it became completely true. Of course, the more precise is again something like this formula, the more precise proof, but it is more or less this. Everything else is also some not too difficult exercises in elementary functional analysis, and I want to skip it. Okay, so here is the result, that when we take an ergodic average of some function from L1, we have a limit. And this limit is an invariant function. Well, the question is, so there are several questions. First of all, assume that we have just the usual situation when we have no measure, we have just, for example, some good, for example, continuous or maybe smooth map of some nice set. So something like interval or maybe manifold or something like this. Can we apply something like an ergodic theorem in this situation? So the question is, how can we see any invariant measures? The second question is the following: can we somehow find these invariant functions? Are there many of them for a given function and for a given measure? And the third question is, okay, maybe there is one measure which is invariant, but maybe there are several measures. So what is a natural situation? So this is the questions I would like to start discussing today, and we will continue next time. So the first thing is how to well, let's say construct, but the word construct here is a bit misleading, because of course we don't present any of them. They will be some sort of non-explicit or some sort of implicit construction. Well, this is a called Krillo theorem. That is the following. Let T be a continuous So just a moment. Yes, of symmetrizable compact set. So just take a compact set in some metric space and assume that T is a continuous map from X to X. Then there exists mu, which is Borel probability measure on X, and mu is T invariant. So there is at least one invariant measure. Let me recall that the Borel measure is the measure that such that all open sets are measurable. Okay, so how to prove this? The idea is the following: that the set of the continuous functions of this on this X is separable. Proof. So C of X is separable. So this is the phi J dense subset. So there exists a countable dense subset in the set of continuous functions on X. Then what I want to say is that if I find some good functional on the continuous functions, then it is also always something. That the set of the functionals. So let's see X. The set of the bounded linear functionals on C of X is just the set of all signed measures. So, and if we have this, so this means that for such a functional, there exists some measure such that G of F is an integral of F d mu, where mu may be it may be not necessarily a positive measure. So for the measure of some sets can be negative here. And so from this, this is Ergodic theorem. And so what I want to do, I want to construct such a functional that such that first of all the measure that reflects it that corresponds to it is first of all normal non-negative measure, and second I want to check that this functional is corresponds to the invariant measure. And the idea is the following: you can just consider the sequence the sequences. Well, take some point X. X. And then we can consider the ergodic averages for this X of these functions. So we can consider, let's say, phi GM is just a number. Yes, so it's a number, and it is a 1 over m. Of all this. These are sequences, so we can let's write it down as follows: phi g. This set is bounded because everything is not more than the norm of phi j in the set of C of x. So because every continuous function is bounded by some, on the compact is bounded by some value, then when you take any point and take averages of this sort, it is all phi j. Then this is also bounded. And therefore, you can take the subsequence that converges. And moreover, so there exists n1 so there exists m such that phi g m1 of n phi 1 converges. Then we can take a subsequence such that for phi 2 we have also a convergence. Then we can take some subsequence such that for phi 3 we have also convergence, and so on. Then we take the diagonal in this construction. Let me skip the precise definition. I guess the general construction is clear, that if you have such subsequent convergence, then you can take the diagonal. So you take the first element from the first sequence, then you take the second element from the second sequence, and so on. And then for this, and since on every step I go, so then for this diagonal, all numbers except maybe finite number of all of this is a subsequence of the corresponding sequence on each row. We have that for this subsequence there is convergence. So there exists m, well, let's say diagonal n, such that phi j m diagonal n converges as n tends to infinity to phi j star for any j. This is a key argument. Now I want to say that for any function phi in C of x, we have the same convergence. There exists the limit of as n tends to infinity and we define this limit as j of phi. Why is it so? Well, because if you take this phi, there exists some j such that phi minus phi j, the norm is less than epsilon. Therefore, so of course the Sm of phi, you can express it as Sm of phi j plus Sm n delta of phi minus phi j. Okay, this is by absolute value not more than epsilon because of this. Because when you average a function that is bounded by epsilon, the averages are also not more than epsilon. And for this guy, and therefore its upper limit minus its lower limit is not more than 2 epsilon. For this guy, upper limit is just equal to the lower limit because it converges, and therefore for the sum we have that upper limit minus lower limit is vice versa. Is also not more than 2 epsilon. And since epsilon is arbitrary, we have that this difference is in fact 0. So we have a convergence. Now we want to check some conditions on on our functional. So g of phi is the limit of the ergodic averages, but along some subsequence point x. Maybe I should write it down everywhere of x. Okay, then this is linear. That's clear because if you take the sum, then the ergodic averages are also linear, and then you go to limit, it is also linear. Then the second, it is that it is bounded in norm, so the absolute value of g phi is not more than the norm of phi. Again, because the same is true for SMN for any ergodic average, and then you go to pass to the limit. Then it is non-negative for non-negative function. Again, just clear. And all this, so the first two says that g of phi is an integral over the integral with respect to some measure, some signed measure, and this means that mu is not signed measure. Is just a regular measure that assigns to every set some non-negative number. So we have constructed this measure. Oh, and by the way, one more property is that g of phi in composition with t equals to g of phi. This is this property is also quite straightforward because you see when you take the when you take this, you have the sum. So in these two sums, almost all components cancels out. Almost all summands cancels out, and you have just 1 over m phi over t m of x minus phi of x. And because so for a continuous function, we have that this continuous function is bounded, so this definitely goes to 0. And so when we pass to a limit, or even to a limit under with respect to some subsequence, it doesn't matter. This goes to 0, so we have this. So this means that mu is. This means that the integral of that we have this, and in fact, this is again a bit of functional analysis. This implies that phi is that mu is T invariant. So that if the integral, if such, so if for any continuous function this is true, then for any, say, measurable function this is also true. So for any function from L1, because you can pass to a limit, can approximate any function by function in L1. And if this is true for any function in L1 in particular, it holds for the functions that are for indicator functions, and therefore have the measure of each set equals to the measure of its preimage. This is the proof of this part. And so we have constructed this invariant measure. Let me conclude with the following question and partial answer. Are there uniqueness? The answer is no. Or to be precise, sometimes yes, sometimes no. Let me state it as a theorem. So for R alpha, let me recall that this is our first example. So this is a map of a circle where alpha is, well, let's start with rational. If alpha is rational, then we have some power that just is an identity map. So you can say that if alpha is rational, so alpha is P over Q. You can do this as follows. You can just take the measure on the 1/q of the circle. Well, maybe you just say this. And then you can copy this. Maybe you want that the measure on this is equal to 1 over q. Just scale it down so that this holds. And then you just copy this measure. Formally speaking, you take the push forward under the corresponding map, but doesn't matter, to every other part of the circle. You get this, this, and so on. So you have q copies of this measure, and it is clear that the measure u plus well, u in composition with t with r is invariant. So just because so if you can consider any set, split it into parts that belongs to each of this semi-intervals, and then each such set is moved by R alpha to the set to the part in the corresponding part in the different semi-interval, and therefore its measure is the same. But this is not so interesting, because this is definitely some sort of pathological situation when you have some power of such that our map is identity. This is not interesting. Well, so the next case is R alpha, where alpha is irrational. So this is the first part, and this is the second. In this case, the Lebesgue measure is the only invariant measure. This is not so trivial, but let me explain this as follows. I want to show that the measure of so consider any invariant measure. I want to prove that the measure of say an interval is equal to its length. Let's take this interval. I want to prove that this interval is that its measure is almost is more or less its length. So take some approximations. To do this, I want to use the following. If I take I apply alpha some number of times, then I can move this interval by an almost arbitrary angle, maybe with some accuracy. So, for example, what I want to do, I take this interval, then I take some shifted interval with very, very small gap between them. It is possible because alpha is irrational. Then I take another such interval and another such interval, and so on. And therefore, so I can say the following, that if, for example, I is, so its length is less than 1 over q, then from this figure, it follows that the measure I is less than 1 over q. Why is it so? Let me explain this again. Because if it is so, then I take q copies of this interval, of the same measure, of course, of the same measure mu. And they are disjoint, and therefore the measure of entire circle, which is 1, is less than q times the measure of I. And therefore I have this. So maybe. Moreover, I can repeat this I can generalize this and take not one covering, but say if I want to say that I is less than P over Q, and I want to prove this, then exactly the same argument works, but I want the cover the circle not once, but P times. So I just again do this, but I cover the circle but such that every point is covered but not more than P of the copies. And then I get this exactly by the same argument. And therefore it is, and of course I can also say prove the similar things like this. And because I can just pass to the complements. And from these arguments, I can prove that the measure of every interval equals its length. Well, straightforwardly, it is, I need to figure out how to deal with strict and non-strict inequalities, but just approximating some interval from above and from below, and you will find that this is okay. So this is a sketch of the proof. So there are some maps that have only one invariant measure. There are, in fact, there are quite many of them, but this is mostly not the part I want to discuss. And there are others. For example, let me say that our map E2 that maps x to 2x has many invariant measures, and we'll see next time why is it so. In fact, the set of these invariant measures is, I guess, almost impossible to describe in some constructive way, because there are too many different types of them. So this is some model of the maps that we want to study later. But the next time we'll discuss a bit more of general theory, and then we will want to discuss how this theory is related to the limit results in probability theory, to the law of large numbers, to the central limit theorem, and this is what. And then we will want to discuss: is it true in the more general context for some more general class of systems? So, and for today, this is all. If there are no questions, let's stop here.